elementary school, where I'm sure at some point you were given a rectangle and asked to determine the rectangle's perimeter and area. Of course, to get the perimeter, you added up the lengths of the four sides. So the perimeter here would be 5 plus 2, or 7, and another 5 plus 2, or 7. The perimeter, we would say, is 14. And of course, to get the area of a rectangle, you multiply the length times the width, and 5 times 2 is 10. But perhaps you had a math teacher like I did who was a stickler for indicating units of measure. When we're talking about perimeter, we're talking about a measurement of length, and the length around this rectangle is 14 feet. And this measurement of 10 is not a measurement of length, but rather a measurement of area. The area of this rectangle is 10 square feet. Or we could also indicate this as 10 feet squared. When we add 5 feet plus 2 feet plus 5 feet plus 2 feet, we're essentially combining like terms. There's a total of 14 feet. When we multiply 5 feet times 2 feet, 5 times 2 is 10, and feet times feet is feet squared. We're going to be looking at a bunch of things today, but our main focus in this lesson is going to be learning how to indicate the correct units of measure. Let's first of all establish that in calculus, you're often given a function and you're typically asked questions about either that primary function, its first derivative, or its second derivative. You'll see sometimes, especially when we move on, that the function we're given could be the first derivative. But regardless, we're often asked questions about either the primary function, the first derivative, or the second derivative. Of course, if I know f of x, evaluating f of 3 is a cinch. I just plug 3 in for x. 3 squared is 9, and 9 plus 3 is 12. If I'm given f of x and asked to evaluate f prime of 3, well, I first need to get the derivative. Once I know f prime of x, to evaluate f prime of 3, I simply plug 3 into the derivative. 2 times 3 is 6, and 6 plus 1 is 7. And of course, to evaluate f double prime of 3, I'm going to need to get the second derivative. Well, the second derivative here is 2, so apparently it doesn't matter what you plug in, the output is always going to be 2. Now, of course, this isn't a word problem, so units aren't appropriate, but what we're going to learn today is that if you know the units of any one of these functions, well, you're going to see that you'll know the units of all of them. In calculus, we deal with 3 types of functions. We deal with primary functions, we deal with first derivatives, and we deal with second derivatives. We're going to see that the output of a primary function is always a quantity. The output of our first derivative is always a rate of change. And the second derivative is the most abstract. The output of the second derivative is always a rate of change of your rate of change. Let's start by looking at a simple example. Imagine a car is driving at a speed of 60 miles per hour. It's never speeding up and it's never slowing down. Well, here, f of x is a primary function that will give us the distance the car has driven at any time we want. I could evaluate f of 1. 60 times 1 is 60. I know after 1 hour of driving, this car has traveled a distance of 60 miles. I could evaluate f of 2. 60 times 2 is 120. I know after 2 hours of driving, this car has driven 120 miles. F of 3 is, of course, 60 times 3, or 180, and the output of this function is miles. It's a quantity. It's a number of miles driven. In this function, you plug in the x value of hours, and you get the y value of miles. Now, fortunately, at this stage of the game, we're already good enough at calculus that we know how to get the derivative of f of x. F prime of x is 60, and let's take a look at what that graph looks like. Of course, the graph of f prime of x equals 60, or if you want to imagine y equals 60, it's just a horizontal line at 60. In this function, you still plug in the x value of hours, but notice you don't get a distance. At time 1, our output is 60. At time 2, our output is 60. It doesn't matter what we plug in, the output is always going to be 60. That's because the output of a first derivative is not a quantity, it's a rate. It's a rate of change. The output of the first derivative is not miles, but rather miles per hour. I'm going to say f prime of 3, at time 3, the car is driving 60 miles per hour. In the primary function, we plugged in hours, and we got miles. In the first derivative, we plug in hours, but our output is miles per hour, y over x, or slope. Let's take a look and try to make some sense of the second derivative. Of course, the second derivative, the derivative of 60, is 0. So of course that means that f double prime of 3, or f double prime of any number for that matter, equals 0. All right, let's see if you can follow this logic. In the first derivative, the output was miles per hour. So in the second derivative, the output's going to be miles per hour per hour. Now, this probably isn't the best example, but let's try to finish making some sense of it. We know at time 3, the speed of the car was 60 miles per hour. Well, if f double prime is 0, that just means an hour later, the speed is not going to change. The change in speed will be 0. It will still be going 60 miles per hour. I want to show you another way we could write miles per hour per hour. This is still miles per hour per hour. Let me put this hour over 1, and now let me divide these fractions, or let me multiply miles per hour by the reciprocal of hour over 1. And maybe you see another way we could say this is miles over hours squared. And there you have it. The output of the primary function was miles, the output of the first derivative is miles per hour, and the output of the second derivative is miles per hour squared. You're going to see that that pattern will always hold true, and as long as you know the input and output of one of the functions, well then you should know the output of all of the functions. Let's suppose I planted a tree in my backyard, and I have this function f prime of x, which gives me the rate of change of height of the tree as time goes on. When the tree's 1 year old, it's growing at a rate of about 8 feet per year. And when the tree's 2 years old, it's growing at a rate of maybe, only 5 feet per year. And then when the tree's 3 years old, it's growing at a rate of maybe 4 feet per year. Well, if I know the output of f prime of x is feet per year, then I should know the output of f of x and f double prime of x as well. The output of f of x should be feet. The output of f prime of x we already know is feet per year, and the output of f double prime of x should be feet per year squared. My primary function gives me a quantity, how many feet tall the tree is. My first derivative gives me a rate, the rate the tree is growing, and my second derivative gives me a rate of a rate, or a rate of change of the rate. In this example, we have a tank of water, and water is being drained through this spigot here, and g of t will give us the gallons of water in the tank, where t is being measured in minutes. G of t is my primary function, so function g is going to give us a quantity, how many gallons of water are in the tank. Let's see how many gallons there are at time 1. If I plug 1 in, 1 cubed is 1, minus 4 times 1, 1 minus 4 is negative 3, and negative 3 plus 10 is 7. I'm going to say after 1 minute of draining water, there are 7 gallons of water in the tank. Let's see how many gallons there are at time 2. 2 cubed is 8, and 2 squared is 4. 4 times 4 is 16. Well, 8 minus 16 is negative 8, and negative 8 plus 10 is 2. Apparently at time 2, there are only 2 gallons of water left. Well, we're going to see here that water wasn't being drained at a constant rate. Perhaps as the water was being drained, someone was tightening the spigot, so it started off coming out pretty quickly, but as time went on, the rate of change slowed down. To evaluate g prime of 1 and g prime of 2, we of course need to get the derivative of g. And g prime of t would be 3t squared minus 8t. Let's see what g prime of 1 is. If I plug 1 in for t, I get 3 minus 8, or negative 5. And my output here is going to be a rate. It's going to be measured in gallons per minute. At time 1, water was draining 5 gallons per minute. Let's go see what the rate was at time 2. 2 squared is 4, 3 times 4 is 12, and 12 minus 8 times 2, 12 minus 16 is negative 4. As you can see, someone was tightening the spigot. At time 2, the water is only draining at a rate of 4 gallons per minute. Of course, to evaluate g double prime of 1 and g double prime of 2, we need to get our second derivative. The derivative of 3t squared is 6t, and the derivative of 8t is 8. G double prime of 1 is 6 times 1, or 6 minus 8, negative 2, and my output is gallons per minute squared. G double prime of 2, 6 times 2 is 12, and 12 minus 8 is positive 4. Or we could say positive 4 gallons per minute squared. The output of my primary function is gallons, the output of my first derivative is gallons per minute, and the output of my second derivative is gallons per minute squared. In calculus class and in physics, we often encounter these functions x of t, v of t, and a of t, where x of t is our primary function, and it gives us the position of an object. V of t is our first derivative. It gives us our rate of change, or velocity, of an object. And a of t is our second derivative, and it gives us the acceleration of the object. Let's talk a little bit about velocity and acceleration. First of all, sometimes we have a positive velocity, and sometimes we're dealing with a negative velocity. In the morning when I'm driving to school, I can describe my velocity as positive 70 miles per hour because my distance from home is increasing. My distance from home is getting larger. Then of course in the evening on my way home, I can describe my velocity as negative 70 miles per hour because my distance from home is decreasing or getting smaller. Notice that when I'm driving to work in the morning or home in the evening, I'm driving the same speed. Both times of day, I'm driving at a speed of 70 miles per hour. We can say speed is the absolute value of velocity. Let's try to make some sense of this concept of acceleration. In the morning, I'm driving positive 70 miles per hour. Well, if I apply an acceleration of positive 10 miles per hour or positive 10 miles per hour squared, that just means that 1 hour later, my velocity will be positive 80 miles per hour. If, on the other hand, my acceleration is negative 10 miles per hour squared, well, that just means in an hour's time, my velocity will only be positive 60 miles per hour. When my velocity was positive and my acceleration was positive, I hope you saw I was speeding up. When my velocity was positive and my acceleration was negative, well then I was slowing down. In the afternoon, my velocity is negative 70 miles per hour. My speed is still 70 miles per hour, but the velocity is negative. That indicates we're traveling in the opposite direction we were in the morning. Now in the afternoon, if I apply an acceleration of positive 10 miles per hour squared, that just means in 1 hour's time, my velocity will become negative 60 miles per hour. And if my velocity is negative 60 miles per hour, that means I'm traveling at a speed of 60 miles per hour. Notice, when my velocity was negative and my acceleration was positive, I was slowing down. If my velocity is negative 70 miles per hour and I apply an acceleration of negative 10 miles per hour squared, that means in 1 hour's time, my velocity will be negative 80 miles per hour. And if my velocity is negative 80 miles per hour, that means my speed is 80 miles per hour. Notice if my velocity and my acceleration are the same sign, that means I'm speeding up. An object is speeding up when its velocity and acceleration have the same signs. An object is slowing down when its velocity and acceleration have different signs.